So hello and welcome to another digital design class. In the previous class, we finished complements and different type of binary code systems such as BCD, ASCII codes and gray codes and so on. And we mentioned where do we use these binary systems in the computer system? What does a register mean, and how does a BCD code, for example, or ASCII code work in a computer system? Today, we're going to start with binary logic, and we're going to speak about binary logic gates. From next week, we're going to have our labs. In the class, you have your computers. For the online students as well, you can use any simulating tools. I will walk you through how you do that on your computers, and we will practice some logic gate design, and I'll give you some examples, and we will do lab number 1 from next week. So the definition of binary logic gates, they consist of binary variables and a set of logical operations. The variables are designated letters of the alphabet, such as A, B, C, or X, Y, Z, etc. And each variable can have only 2 distinct possible values, 1 or 0, because it's a binary logic, so it couldn't have anything besides 1 and 0. And the 3 basic logic operations are AND, OR, and NOT. The AND operation is represented by a dot or by absence of any operators. And for example, A dot B, or we will write it AB like this. So AB is equal to C, or A dot B is equal to C. And we call it AND, so it's A and B. For AND logic, if A and B are both 1s, then the answer would be 1. If one of them is 0, the answer would be 0. The next operation is the OR operation, and we show it with the plus sign. So A or B, or A plus B, is equal to C. So this is the OR operation. This is the AND operation. And the last one is the NOT operation. And we show it with a bar like A naught, or we show it with prime. So this is the NOT operation. So whatever A is, if it's 1, A naught would be 0. If A is 0, A naught would be 1. It's not A, so we call it A prime or A naught. And for the OR operation, it's A or B. So if one of them, for example, is 1, the answer would be 1. Now, we show these binary logics with the binary logic gates. We have AND, OR, and the NOT logic gate. The AND logic gate we showed like this, OR we showed like this, and the NOT is shown like this. For an AND logic gate, if X and Y are both 0 AND with 0 is 0, 0 AND with 1 is 0, 1 AND with 0 is 0, and 1 AND with on is 1. So basically, it's like a multiplication. You multiply 1 by 1 is 1, 1 by 0 is 0, 0 by 1 is 0, and 0 by 0 is also 0. How many inputs do I have? 2. So I would have 2 in the power of n, or in other words, 2 in the power of 2, I would have 4 possible combinations. 0, 0, 0, 1, 1, 0, and 1, 1. And it's going to be 0. The answer would be 0 unless both of them are 1. Now, the OR logic gate is going to be shown with the plus sign. So Z is equal to X or Y, or X plus Y. and we show it with this symbol. And for an OR logic system, again, doing 2 in the power of 2 is gonna have 4 different combinations. 0 plus 0 gives us 0. 0 plus 1 gives us 1. 1 plus 0 gives us 1. And 1 plus 1 gives us 1. So you can see here, 1 plus 1 is not 1, 0, it's 1. It's A or B or X or Y. And you can see that it's 1. The answer is 1 unless both of them are 0. And finally, we have the NOT gate or the NOT binary logic. And we show it with the prime with the bar. And whatever X is, Z is the opposite of X, or it's not X. Z is not X. So if X is 0, Z would be 1. If X is 1, Z would be 0. Sometimes we show, in some books, we show the NOT gate simply with a circle. This is also a NOT gate. The symbol is also shown with a circle. So the way that we show the AND or OR gate with the switch circuit is like this. An AND gate is like 2 switches connected in series. The OR gate is like 2 switches which are connected in parallel. So when the switch is on, it means it's 1. When it's off, it means it's 0. So if one of them is on and one of them is off, so imagine this one, A is on and B is off. So A would be 1 and B would be 0. Would the light turn on? No. So the answer would be Z would be what? Or C, let's say the lamp is C. It would be off or 0. What if A is 0 and B is 1? Same, this would be 0. What if both of them are off? Still 0. And what both of them are on? C would be equal to 1. So the only condition that we can turn on this lamp is that if both switches are closed or are on. The OR switch is like having the OR logic is like having 2 switches in parallel. So let's say A and B, and then we have C. So if A is closed, it means it's 1 and B is 0. Would the light turn on if one of them is closed? Yes, so C would be equal to. If A is 0 and B is 1, C will still be 1. But if both of them are 0, meaning both of them are off, C would be equal to 0. And if both of them are on, B is equal to 1 and C is equal to 1, then this would be equal to 1. Let me draw it in another way. So A and B. If A is on, B is off, A is off, B is on, A is on, B is on, and A is off and B is off. And this is the only situation that would turn off lamp. Now, how does a binary logic gate logic system even work? And I've already mentioned this. A binary logic system works based on the voltage, okay? So the logic of 1 means we have a positive voltage. Usually, for this case, it's above 2 volts. And anything below 1 volts is the logic of 0. So again, anything in this area is a logic of 1. Anything in the blue area is a logic of 0. And in between that, we have an undefined region. And I'm going to show this one with black. Why do we need an undefined region? You remember I explained why do we need this region? Yes, and to reduce error. If I didn't have that and I just had the line that separated these two regions, then easily if I had just a simple like small noise, then the logic would go from 1 to 0. So I need to have a gap, a transition gap, a threshold between a threshold region between these two logic gates, so I will reduce error. Okay. And on the right, you can see the logic of 0. Again, anything below 1 volts, and the logic of 1 is anything above 1 volts. So what happens if the signal is like this? What happens to this part? In the middle, this is undefined. It's nor 0, it's nor 1. Okay, so if we have something in the middle, we don't know if it's 0 or if it's 1. It's nor 0 and nor 1. It's undefined. We usually should with X, it's, unacceptable. We don't count it as 0, we don't count it as 1. It's none of those. Is it clear? So anything that it's in this region, it's nor 0 and it's nor 1. It's nothing. So this here shows a transition between the when we have different inputs for different logic gates. We have the inputs here are X and Y. X and Y. And if we have an AND gate, if X is 0 and Y is 0, for an AND gate, X and Y is going to be 0. So X times Y gives us 0. Again, if X is 1 and Y is 0, again, we're going to have 0 in the answer. If both of them are 1, the answer would be 1. If both 1 is 0, 1 is 0, and 0, 0 is also 0. We usually show it like this, which is a binary signal. And for the OR gate, if AND is 0 and Y is, if X is 0 and Y is 0, then or the result would be 0. 0 plus 1 is going to be 1. 1 plus 1 is 1. 1 plus 0 is 0. And 0 plus 0 is 0. And for the NOT gate, it's not X. So everything that X is not X would be the opposite. So 0 goes to 1. 1 goes to 0. 1 goes to 0. 0 goes to 1. And 0 goes to 1. We can also combine these gates as well. If I combine a NOT gate with an AND gate, so if I put an AND gate at the end of a NOT gate, I would have what we call a NAND gate. A NAND gate or a NOT AND gate creates a new gate that we show it with this. It's an AND gate that has a circle at the end. So this is a NAND gate. Let me insert. So I can combine an AND gate with a NOT gate, and what I get is a NAND gate. And for a NAND gate, if I have the inputs X and Y, and the output would be Z, the table will look like this. Again, a NAND gate is a NOT AND gate, meaning it's an AND gate connected to a NOT gate. So let's solve this together. If X and Y are 0, 0, what would the output be? What would the output of the AND gate be? 0. And what would the output of the NAND gate be? 1. So 0, 0 gives us 1. What if X is 1 and Y is 0? Again, 1, 0, 0 and still gives us 1. What if x is 0 and y is 1? Still gives us 0 and the output would still be 1. Am I correct? Now, what if both of them are 1? 1 and with 1 gives us 1 and the output would be what? So 1, 1, 0. So if we go to the back to the AND table, you can see that a NAND table is completely opposite of an AND table. So I'm going to put the outputs for the NAND. It's going to be 1, 1, 1, 0. So a NAND gate is complete opposite of an AND gate. Is it clear? Can I go to the next one? Okay. I can also combine the NOT gate with an OR gate. So if I have an OR gate and I add a NOT gate at the end, I'm going to have what we call a NOR gate. So a NOR gate is a NOT OR, and we show it like this. We simply put a circle at the end of NOR gate, which is a NOT combined with the OR gate, or combined with a NOT gate. So let's solve this for an OR gate. Again, for an OR gate, if I have 0, 0 for x and y, what would the output be? 0 OR with 0 is going to be 0. The NOT would be 1. If I have 0, 1, the answer would be 1. So 0, 1 would be 1, and the output would be 0. If I have 1, 0, this output would be 1, and the final output would be 0. And if I have 1, 1, this would be 1, and the final output would be 0. So 1, 1 gives us 2. Again, 0, 0, 0, 1, 1, 0, and 1, 1 gives us 0, 1, 1, 1. So it's a NOT OR what we call a NOR gate. And if you look at this, you can see that a NOR gate is the complete opposite of an OR gate. So whenever we have a 0 in the OR gate, we're going to have 1 in the NOR gate. And whenever we have a 1 in the answer to the OR gate, we're going to have 0 at the NOR gate. We show the NAND gate with this symbol, A, B, and this is the NAND sample. We put a bar on top of it. And we show the NOR gate with this. I'm going to go back, A, B bar, or A NAND with B. And for the NOR gates, we show it with A plus B bar. So as you can see, we can combine a NAND gate with a the AND gate with a NOT gate will create a NAND gate. We can combine OR gate with a NOT gate and create a NOR gate. And also we can have digital logic gates with multiple inputs. We saw digital logic gates with 2 inputs, which are the AND and OR gates, and 1 input, which is the NOT gate. We can also have the AND and the OR gate with multiple inputs. For example, 3 inputs or 4 inputs, or 5, 6, 7 inputs. And for this example, we have on the left, we have an AND gate with 3 inputs. And we have on the right, we have a OR gate with 4 inputs. So if we have 3 inputs, if A is 0, B is 1, and C is 1, what would the answer be? So F would be A and with B and with C. So it's going to be 0 and with 1 and with 1. It's going to be equal to what? 0. If it's like we are having C, A and B as 3 switches connected in series. If even one of them is open, those two are close, so the light would not turn on. Okay. Now the one on the right, if A is 0, B is 0, C is 0, and D is 1, what would the answer be? G. Yes, it's going to be 0 plus 0 plus 0 plus 1, which gives us 1. Again, it's like having 4 switches in parallel. If even one of them is closed, it's like all of them are closed, so it doesn't make any difference. Is it clear? Yes. What if I have the AND gate with 3 inputs, but I add a NOT gate at the end and I create a NAND gate? So now it looks like this. And what if A is 1, B is 0, and C is 1? What would F be? And basically, this is actually F prime. What is F and what is F prime? Output. Yes, correct. So this is like having an AND gate connected to a NOT gate. So if I have 1, 0, 1, the result would be 0, the final result would be 1. So this F prime would be equal to 1. Now let's solve another example. Now let me give you another example. Imagine if instead of 4, I have 40 or 25 inputs. So A, B, C, D, going down to Z. So I have maybe 20, 30, inputs. And what if A is 1, but the rest of them is 0? What would the output be? 1. Perfect. So if even one of them is, so sigma of A to Z, if in A is 1, then the answer would be 1. Okay. And what if instead of 3, I have again 20 or 30 inputs for an AND gate, and A is equal to 0? What would the answer be? 0. So F would be the multiplication of A to Z. And if one of them is 0, the answer would be what? 0. Okay. So for an OR gate, one of them is 1, the answer would be 1 regardless. So if you see this in a, question, only one of them needs to be 1. And only situation that the output is 0 is if every single input is 0. And for an AND gate, it's the opposite. If every single input is 1, then the output would be 1. If just one of them is 0, the output would be 0. Is it clear? Can I go to the next slide? So another type of gate that we have, which is important, is called the XOR gate. So we show it with the plus sign in the circle, this sign over here. And for the example here, C is equal to A, XOR with B. And we show it with this symbol over here. It's an OR gate, and we have like a parenthesis in the input. For an XOR gate, if A and B are 0, the output would be 0. If A is 0, B is 1, the output would be 1. If A is 1 and B is 0, the output would be 1. And if A and B are 1, the output would be 0. So do you see a pattern here? What is our pattern? If A and B are equal, then C would be equal to what? 0. Thank you. If A and B are different, then C would be equal to 1. So if the inputs are the same, output would be 0, meaning there's no difference between them. If A and B are different, one of them is 0, one of them is 1, then the output would be 1. Now, we can also combine the NOT gate with the XOR gate, and we create a gate called the XNOR gate. And the XNOR gate is technically when you add a NOT gate at the end of the XOR, and then we would create this XNOR gate. And we show it with this. We have an XOR gate, and we have the circle at the end. So Y would be equal to A X or B bar. Yeah, you put a bar sign on the top. And that is equal to, and I'll show you that in the De Morgan's law and so on, that it's equal to A and B plus A and B bar, or A dot B plus A bar dot B bar. Now an XNOR gate is the opposite of an XOR gate. If A is equal to B, then C or Y, the output, would be equal to 1. If A and B are different, then the output would be equal to 0. So it's the exact opposite of an XOR gate. Is it clear? Yes. Okay. Now let's solve some practice problems. Oh, and another gate that I want to mention that it hasn't been mentioned. It's if we have this gate, this is called a buffer. A buffer gate, if you give 1 in the input, you get 1 in the output. If you get 0 in the input, you get 0 in the output. Okay. And we just have it for, preventing the load to have the load resistance to be converted to the input. There are different applications for the buffer or for shifting something. But the buffer is looking like this. And if I add the circle at the end of the buffer, it becomes a NOT gate. Okay. Now for the first question, I have this gate, but I connect the inputs together and I give it to X. I want you to draw the truth table for this. For X, the input, and Z, the output. I have a quick question. When do you have time for the first exam? Did you think on when you can take the first exam? Mm. What about end of September, September 30th? Does that work for you? Check with what your other classes, and if you don't have an exam, your first midterm exam is gonna be September 30th, okay? I'll post an announcement. Well. So what is the answer to this? If X is 0, gonna have 0, 0 in the inputs, and 0, 0, the NAND would be 1. What if X is 1? Then we're gonna have 1, 1 connected to here, and Z would be 0. So if X is 0, Z is 1. If X is 1, 0, 0. This looks similar to another gate. What gate is this? It's a NOT gate. So a NAND gate that has when the inputs are tied together is equal to a NOT gate. So this is also a NOT gate. Is it clear? Yes. Now let's draw another one. I have a NOR gate, and I want to connect the input together, and I'm going to call this X. So this is a NOR gate with its inputs tied together. Draw the truth table for it. Okay, what is the answer? What is X? If it's 1, what would Z be? 0. If X is 0, Z would be equal to. So 0, Z is 1, 1, the Z is 0. Again, this looks like what? NOT gate. So this is equal to a NOT gate, which is equal again to what? The NAND gate with its inputs tied together. So all of these three are equal. Now, what I want you to do, I want you to build an AND gate by just using NAND gates. So build AND gate just using NAND gates. Did anyone solve it? How many gates do I need? 2. Perfect. So what I can do, I can put a NAND gate and then connect it to another NAND gate, which has its inputs connected. So this is a NOT NAND, which is equal to an AND gate. Okay. Again, if X and Y 0, 0, for example, is equal to 0, 0, 1 is 0, 1, 0 is 0, and 1, 1 gives us. You can check all steps. I'm just going to check 0, 0. So 0, 0 gives us 1, and 1 gives us 0. So combining these two gives us an. Okay, let's solve another one. This is an OR gate, this is an XOR gate, and this is a NAND gate. This is 0, this is 1, this is 1. What is the output F equal to? Yes, XOR. I'm sorry, XNOR. Makes it XNOR. I did it right. Yeah. Pen doesn't work well, so it shifts. So it's an XNOR, not an XOR. And the last one is an AND gate. Did you all solve it or you need a few minutes? What is the answer? 1. Everyone got 1? Yes. Okay, let's check it. So 0 OR with 0 gives us 1. Let me draw it with. And this 1 goes through this NOT gate becomes 0. 0 XNOR with 1. What does it give us? 0. And at the end, 1 and 0 and NAND would be equal to what? 1 and with 0 is 0, so the NAND would be equal to 1. Now let's solve another one. If the input is 1, what is the output? This is an XNOR, this is an XOR, this is a NAND. What is the answer? 1, okay. So the 1 goes through the NAND gates. It's like a NAND gate becomes 0. 1 goes through this NOT gate, it becomes 0. 0 goes through the XNOR gate, which the inputs are tied together. And for an XNOR gate, which the inputs are tied together, the inputs are going to be the same, so the output would be equal to 1. And 0 with 1, the output would be what? If they are different, it's going to be equal to 1. And let's solve another one. This is the last one. Oh. A NAND gate, 3 inputs, and one of them is connected to a NOR gate with 2 inputs. Another one is connected to an XNOR gain connected together. And one of them is connected to an XOR gain gate connected. And all of them is connected to one. What is the output F equal to? So the first one, it's obvious. One passing that this NOR gate is going to be 0. So regardless of what the rest is, F would be equal to 0. Even if I didn't know this one, this is one of them is an X or one of it is an XNOR. So they would have opposite answers. So if one of is 1, the other one would be 0. So again, one of these would definitely be 0. The output would be equal to 0. So I don't even need to even check all of the inputs. Okay. Now the next question, if the output F is equal to 1, what are the inputs? What are the possible inputs, X? Does anyone have the answer? What did you get?
Got 0.
0. Okay. So the output is a X NOR gate. And when X NOR gate is 1, it means that both the inputs would be equal. So this could be 0, 0, or it could be 1, 1. Let's solve it first for 0, 0. So if this is 0, this is a NOT gate, this would be 1, and this is also, this is an X NOR gate, which the inputs are connected together. And when the X NOR gate, the inputs are connected together, it means they, and the output is equal to 0, it means that A and B are different, which in this case cannot actually happen. So this is wrong. It can't be 0, 0, because if it's 0, the input must be the same, must be different, and here it's obviously connected, so that cannot be the case. Again, because the input should be different, so that could not be the case, therefore it could not be 0. What about if it's 1, 1? Then if that is 1, then the outputs are equal. It could be 0 or it could be 1. And what about if this is 1, this is 0? If this is 0, this should be 1. Again, this is not possible. So this must be 0. So this is 0, and X is equal to 0. Okay. Again, if this is 0, this would be 1, and these two are not allowed to be different. So the input must be 1. So the only answer that we can get is X equal to 0. Is it clear, or do you want me to explain it again? Clear? Okay. That's it for today. Thank you so much. I posted your first homework. You have it, I think, until this weekend or next Tuesday, I think. Tuesday, Thursday, okay, to complete it. And next week we will start with Boolean algebra and how we solve these Boolean logic gate circuits. Thank you so much and have a great weekend.